guys all see this, or should I write bigger? Okay. And a metric space is basically the set S with a distance function. We also call it a metric D, which goes from S times S to R. And this basically means that as an input, D takes in two elements of S and it outputs a real number. So it's the distance between two elements of S. And in order to be a valid metric, there are four properties that D has to satisfy, which is that for any X, Y, Z in the set S, the XX has to equal 0, so the distance from a point to itself has to equal 0. The XY has to be positive whenever X and Y are not equal. So the distance between 2 points is always positive in real life also. So that kind of transfers very intuitively into mathematics. And also the symmetric property that dxy is equals to dyx. The distance from x to y is equal to the distance from y to x. And then the final one is this, we call it the triangle inequality, which is dxz is less than or equal to dxy plus dyz. So this is just how we define a metric space. It's any set S with a function that goes from S times S to R that satisfies these four properties. And that's just a metric space. And I'll illustrate this through a few examples. So the first one is where we have the set R with the metric D, where dxy is equal to the absolute value of x minus y. And we'll just verify these four properties really quickly. So, the distance from x to x is 0. So property 1 is satisfied. Whenever x is not equal to y, x minus y is also not equal to 0. So property 2 is satisfied. Oh, and also, since it's an absolute value, we can say that's greater than 0. And x minus y and then x minus y is equal to y minus x. So the distance from x to y is equal to the distance from y to x. So property 3 is satisfied. And finally, the triangle inequality is the one we're used to when working with the real numbers. So these four properties are satisfied, and R with this metric is a valid metric space. And you'll realize this is actually just the real number line with the generic distance function that we use with the real numbers. So for example, the distance from like 0.2 to 3 on the real number line is just the absolute value of 3 minus 0.2, which is 2.8. So the real number line with the distance function that we're used to, that is a metric space within this formulation. The second one I'll use is the Euclidean n space with this metric where this is equal to the summation of do you guys all know what this means, this symbol? No? Oh, okay. So the real number line, like R1, this is just the real numbers, right? The real number line that we all work, that's just R1. And now if you add a second axis to this, like a second real number line, a y-axis, then you get this plane, and we call this R2 because every point is represented by a pair of numbers. So this point is like 1, 2, this is 2, 1. Every point is two real numbers. And we get R3 when we add like a z-axis to this to make this 3 dimensions. So now every element is represented by a unique combination of 3 real numbers. So like this is like 1, 1, 1. Here's like 2, 1, 1. So every point is a combination of 3 numbers. It's a coordinate space composed of the real numbers, like 3 real numbers. And Rn is kind of a mathematical generalization of this idea where every point is a coordinate is like an n tuple of real numbers. And we just treat it just like every other coordinate. And that things like Pythagoras' theorem, these all apply equally in this n-dimensional space. And if you notice, this expression kind of looks scary, but if you use Pythagoras' theorem, this is equal to just the generic distance function we use. So like, for example, in R2, if we have like 1, 1 and like 4, 5, right? Then like 3, 4, and then we use to get this distance between these points, that's just equal to this formula. So this formula is just the extension of this idea of using Pythagoras' theorem to the n dimensions. It's the generic distance function that we are all used to. And these 4 properties apply. I'll just prove this in R2 since the algebra gets a bit tricky with the n dimensions. So if you have a 2-dimensional space, like a distance from point x to itself is 0, right, on this plane, and it's equal to this distance function that we are all used to. So like the distance is always positive. You can also say, since it's the square root of the sum of squares, it always has to be positive. The xy equal yx, this is just a symmetric expression, so that applies too. And this inequality is a property we're all, hopefully that a lot of you guys know, that like this distance is less than or equal to this plus this. That's the triangular inequality that probably you guys are more used to. So this is also a valid metric space. And now I will point out 2 examples of things that are not metric spaces. So R with the metric D, where dxy equals x minus y, is not a metric space. And can anyone point out which of these 4 properties this metric violates? Property 2, right? Because to give like a counterexample, d2, 3 is 2 minus 3, which is less than 0. So this is not a valid metric. This is not a metric space. One more example. These markers die very quickly. Sorry. Where dxy is equal to x minus y squared. Which of these 4 properties do you think this violates? Triangle, right? Triangle inequality. And to give a counterexample, if you have like 0, 5, 10, then this distance is 100. This is 25. This is 25. So this distance is actually greater than the sum of these 2, which violates the triangle inequality. And so this also cannot be a valid metric. Right. So now that we have this foundation of metric spaces that we can work with, we can point out some specific types of subsets within these metric spaces. So X is just a metric space. Then for any P in X, we call this set to be the set of all points in X that are less than a distance R from point P. So like if you have a point P, and RP would be like this circle of points that are less than a distance R. So like this point would be an NRP. This point would not be here, and we call this a neighborhood of P. That's where the N comes from. And from this idea of neighborhoods, we can derive this idea of limit points. And a limit point is basically for any subset E of X, P is a limit point if every neighborhood, and every is really a key term here, every neighborhood of P includes some element Q of E that is not P. So this means if you have a point P and it's like set of points E, no matter how small of a neighborhood you draw around P, there has to be some point that is not P that is within E. So the points of E get infinitely close to P. That is the idea of a limit point. And from limit points, we get two types of sets. So E is closed if every limit point is in E, and E is open if for all points P in E, there exists some neighborhood NRP that is a subset of E, and this means if you have like this set of points E and any point P, you can draw a neighborhood around it with some positive radius such that this neighborhood is entirely contained within E. And that is this idea of open sets. And actually, before we move on, question is, okay. Hopefully this is pretty straightforward. Yeah. And one property of open and closed sets that we use all the time, first of all, is that NRP is always open. And this is for any radius R at any point P. And just to give a quick proof of this, if we have a point P and this neighborhood, that is a great circle, NRP with radius R. If you choose any point Q within P, notice that the distance between P and Q has to be strictly less than R. And this means that if you draw the neighborhood around Q with the radius R minus D PQ, which is this circle that is like tangent to this bigger one, then this circle is entirely contained within this larger neighborhood. This is a subset of this larger set NRP. And since this argument applies for any Q within this neighborhood, for any Q within this neighborhood, we can draw a neighborhood around Q that is entirely contained within the set. This set must be open. So NRP is always an open set. And the second property is that E is open if and only if the complement of E is closed. Do you guys know what this means, right? Set notation, complement. Okay. So we'll just break this proof down into two statements since we have to prove this direction and also this direction. So to prove this direction, so E is open. If E is open, then EC is closed. So assume that E is open, but the complement of E is not closed. So this means EC has a limit point P that is not in EC, because if every limit point was in EC, then EC will be closed. And we just want to say that this leads to a contradiction. So if E is open, then EC actually must be closed. That is the argument that we are going for. So if EC has a limit point P that is not in EC, so let's just draw this generic set E. This is EC. And there we have this limit point P that is not, that is the limit point of EC, but is an element of E, right? Then, since E is open, there has to be some radius R such that NRP is entirely contained within E, right? But then also because EC is, because P is the limit point of EC, the intersection of NRP with the complement of E has to be non-empty. And these two are contradictory statements. Can you see that? Okay. So this leads to a contradiction. So therefore, EC is closed. And now to prove the other direction, that if EC is closed, then E is open. We can just say, assume EC is closed, but E is not open. And the fact that E is not open means that there is some element P of E that is a limit point in EC. This is a slight bit of a logical jump. Does this make sense? Or should I explain more here? The fact that if EC is closed and E is not open, there has to be some point P in E that is a limit point of EC. Okay. You sure? I can explain. Okay. So assume that there is no such point where of E that is. I'll just do it completely with Z. Okay, so we assume that this is true. If there was no point such that P, E, and P is a limit point, if there was no such point such that P is an E and P is a limit point in EC, this means that for any P and E, right, P cannot be a limit point in EC, so there exists some radius R such that the intersection of NRP with EC is the empty set, because P is not a limit point in EC. If for any radius, the intersection of NRP with EC was not empty, then P would have to be a limit point in the complement of E. So, and actually, if we just take this NRP, since the intersection with E complement is empty, NRP is simply a subset of E. So for any P, we can take some radius R such that NRP is entirely contained within E, so E must be open, which contradicts this point here, right? So if EC is closed and E is not open, then there must exist some P in E that is a limit point in EC. And this statement also contradicts this point because EC must be closed and every limit point must be contained within that set. Good? Okay. Right. This next one was for any collection ON of open sets, the union of all of these sets is also open. And to prove this, no. Okay, you guys know this notation, right? The big, okay. So for any P within this big union, this means there exists some specific open set within this collection, ON, such that P is in ON, right? And since ON is open, we can just take some NRP, such that NRP is contained within ON. And this means that NRP is contained within this entire collection. And therefore, this is open. Okay. And now we take the closed version of this. So for any collection Cn of closed sets, instead of the union, this time it's actually the intersection. So the intersection of all these sets is also closed. And instead of trying to prove this with limit points, really the easiest way to do this is just with using that theorem with the complement. So Cn is closed if and only if the complement of Cn is open, right? By that theorem over there. And so the union of all these complements must be open by this. And actually, just the complement of this set is the intersection of all this. So this is an open set. We take the complement. So this whole thing is closed, which means this set must be closed. So we're just working a lot around with a lot of sets here. And if you guys don't have a lot of experience with set notation, this might be a bit tricky. Is it fine up to here? Okay. So now we're going to, from this discussion, you might get the idea that these ideas of open and closed are absolute, which means if you have this metric space X that's contained within this larger metric space Y and the subset E of X, if E is open in X, then E must also be open in Y. If E is closed in X, then E must also be closed in Y. That idea is actually a trap that a lot of people fall into, which is, and I'll just show a counterexample to show this. So let's say, so we all know that NRP is open, right? Okay. And then NRP is open, this metric space X. So the complement of NRP is closed by that term. We'll be using that term a lot today. So the complement of NRP must be closed because NRP is open, right? But NRPC in the metric space actually, never mind. This example is sorry. I'll give a better one. Let's consider the set of numbers R2 with the metric being the one we talked about before, where I equals 1 to 2. Right? And then let Y be this line, the real number line. So let Y be the set of points. So the metric space X is this whole plane. The Y is a smaller metric space that's composed of the X-axis, right? So Y is a metric space contained within X. And if you consider the set of points, let's say the line between, actually, this interval 0, 1 on the real line. So 0, 1, this interval here, of all the points between 0 and 1, not including 0 and 1, this set is open in X because this is just the neighborhood of 0.5, right, with radius 0.5. So this is an open set within this real line. But if you put this in this larger space X, this is not an open set, because if for any point R you take the neighborhood, there are going to be points out that stick out of this real line. So the entire neighborhood it's impossible to contain this neighborhood within this interval in R. So this set is not open in X. It's open in Y, but not open in X. And there's a theorem that really nicely packages this idea, which is that I'll just write it word for word on the board. The subset of metric space X and E of Y is open in Y if and only if E can be written as the intersection of y and g for some open set g and x. And to prove this, again, since this is an if and only if proof, you have to divide the proof into 2 steps. We'll prove this direction first. So if E is open in Y, so E is open in the smaller metric space of Y, then E must be representable as Y intersection G for some subset G that is open in X. So to prove this, note that for any P in E, we can take some radius RP so that NRP P is entirely contained. Actually, sorry. Oh, yeah. So NRP is entirely contained within E. And this is neighborhood of Y. Because I'll just put RP comma Y to really emphasize that this is neighborhood within Y, because we're only thinking about Y in this case, because E is open in Y. We never said anything about E being open in X yet. So we can take, there's some RP such that the neighborhood with radius RP around point P in the smaller metric space Y is entirely contained within E. And actually, if we just take G to be the union of this neighborhood with the same radius, but this time within X, to be this set, then just note that for all P and E, P is included in this neighborhood. So E is automatically contained within the intersection of G and Y. And at the same time, because NRPY is entirely contained within E, these two have to be equivalent, because if they're, right, should I explain this more? Okay, okay, I'll explain this more. What's the trick? Do you guys understand that the neighborhood within the smaller metric space Y and this larger metric space X is not necessarily equivalent? Okay, I'll start with that. Okay. So if you have a point P, let's say we have the smaller metric space Y and X is the entire plane, right? And I'll draw Y like this. Then if you draw the neighborhood of P with radius R, the neighborhood of P within Y is just this. Because if you recall from the definition of a neighborhood, the neighborhood has to be inside the metric space that's defined in. So this is the neighborhood of P in Y. But in this larger set of X, this whole circle is the neighborhood. So the neighborhoods depend on the context that they're set in. They depend on the metric space they're defined in. I'll just leave that there. Okay. Definition of a limit point. Okay. Okay, I'll give an example of some more limit points, and then we'll come back to this theorem. Any suggestions? Okay. 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 I'll just write the formal definition down first, and then we can talk a bit more about where the confusion is coming from. So P and X is a limit point of a subset E within this metric space if for every there's some Q and NRP such that Q is in E. Okay, so this is the formal definition of a limit point. And to break it down, if we have, let's say, let's just work in Rn since Rn is the easiest, the most intuitive to work with. So if we have X be this plane, the symmetric space of the plane, and E be a subset, then P being a limit point means that no matter how small of an R you take, R can be like infinitely small basically. No matter how small of an R you take, there's a point Q that is contained within the circle. So are you familiar with you're familiar with the concept of limits, right? So this basically means if you guys aren't comfortable with limits, you can just kind of ignore the suggestion, but it's equivalent to saying that there is a sequence of points in E that converges to P without ever becoming P. So there's a sequence like Q1, Q2 of points such that the limit of Qn is equal to P, which says that Q never actually becomes P. So if there's a sequence of points that gets infinitely close to P, then that's a limit point. Does that kind of make sense? Is this better? Okay. I'll just leave this here. Yeah. 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 Every limit point of that set has to be contained in that set. Because let's take that example of the interval from 1.1 to 2, where it's every number between 1 and 2 that is not 1 and 2, right? Then actually you can, if you consider this point 2, 2 is a limit point of the set because you can take numbers to be infinitely close to 2 without actually being 2. 2 is a limit point, but it's not contained within this interval. So this is not a closed set because 2 is a limit point, but it's not within that set. And the same can be said for 1. And if we make this set to include 1 and 2, then this becomes a closed set because every limit point is contained. Yeah. That's not inside the metric space. Can we take the limit of a sequence that is not contained within the metric space X? That it has in real analysis, everything you work with has to be within some metric space, but you can work with a metric space that's smaller, that's contained within a bigger metric space. So if you have a metric space X and a metric space Y, you can think of a sequence of points in this metric space of Y that converges to like a point in X. But in the end, it all has to be contained within some bigger metric space that you can work with. Because if you don't have a metric space, you don't really have a foundation to work with, to do operations with. Okay, any other questions? Okay. Okay, to come back to the theorem. How should I explain this? So we have this metric space X and this metric space Y. This is basically saying this. Let's say that we have this subset E and Y. Then E is open in Y if and only if there's this larger set G that's open in X, and E is the intersection of G and Y. Does this kind of help? So, I'll just explain these two steps separately. So if you have the smaller metric space Y that's contained within X, then if you have it, first of all, so this theorem is two directions, right? So there's two meanings. First of all, if you have an open set E and Y, then it's possible to take a set G that is open in X, such that E is the intersection of Y and G. So it's possible to construct this open set G in X, so that the intersection is E. That's meaning number one. The other direction is that if you have a smaller metric space Y and any set G that is open in X, then this intersection E is open in Y. So that's the two directions of this theorem. So it allows you to transfer this idea of openness between metric spaces. Yeah, that's the key idea. We're trying to transfer between metric spaces here. So to come back to this, the notation is a bit messy, I know. So for all points, okay, so Y is a smaller metric space within X, and we're working this direction. So E is a metric space. E is a set that is open in Y, and we want to construct some larger G that is open in X such that the intersection is E, right? And to do that, we notice that for all P and E, since E is open in Y, we can construct a neighborhood of P in Y that is contained within E. And remember, the neighborhood within Y is not necessarily the same as the neighborhood within X, which is why we make this distinction. And G is just where you take the same radius, but instead of taking the neighborhood in Y, you just take the neighborhood in X and you take the union of this. And since this is a neighborhood in X, it's open in X. And since it's the union of a bunch of open sets, G has to be open. So G is an open set. Okay, I'm getting a few blank. Could you guys explain to me which part of this is confusing? Is it this? Does this not make sense? Can I quiz you on something?
I feel like a lot of us subjects.
Right. Quiz you on something. Of what's it? Something missing. Yeah. I mean, we never really use the like the limit point. You can define with like, yeah. 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 Yeah.
You're assuming you're trying to create a G such that
Yeah. Yeah.
So you're trying to make that.
Yeah. So we're starting from this point and we're trying to end up here, right? And this means so we're trying to show that this G exists. That's what we're trying to prove. And we're doing so via construction. So we're just going to rigorously construct a set G such that it satisfies these conditions to prove that such a G must exist. So this is an existence proof. Okay. Yeah. Okay. We'll try a bit more on this one. And then if it doesn't work out, honestly, we don't really use it a lot later on. So we'll just go on to compactness. But okay. So we have the space Y over to E. And let's just take X completely out of the picture. Just think about Y. For all P and X, we can construct a neighborhood that's contained within E by the definition of open sets. Okay, is this line fine? Okay. So now G, this is just a definition. It's not like, it doesn't involve any logic. It's just, we're constructing a G. G is the union so we're taking the same point, the same radius, but instead of taking the neighborhood in Y, we're just taking the neighborhood in X. And we're taking the union of all those sets. So this is the union of pretty much infinitely many sets, infinitely many neighborhoods. So this is just a definition. It's a construction. It doesn't involve any logic. Okay. Is it a final tier? Okay, it's final tier. The next. So for any P that is within the set E, right? P is contained because this is a neighborhood around P. And the neighborhood always contains the center, no matter how small the radius is. Because it's a circle around the center, right? So P is contained within this set, which means that P is contained within G, right? So E is a subset of G. And E is also a subset of Y, so we can just say E is a subset of the intersection of G and Y. And we want to go one step further. We want to show that these two sets are equivalent. And to show that, assume that E is actually not equal to this intersection, right? And since E is a subset, this means there exists some point P and Y. There's some point like P here, such that P is not in E, but P is in G. Does this make sense? So if we assume that these two sets are, if we assume that E is a proper subset of this intersection, then there must exist some P and Y such that P is not in E, but P is in this set G. And the great thing about this construction here is that G and Y is just this. Because when we moved from the neighborhood in Y to the neighborhood in X, we are just adding a few elements that are not in Y that are in X. So we can move back when we're taking the intersection. Okay.
Y is a proper subset of X.
Right. Y is a proper subset of X. And yeah, I mean, if you really want to make this like a general relation, you can say like NRP XP. This is the relationship that we're working. So if we have a Y in this larger set X and some point P and this neighborhood of P, this whole circle is the neighborhood of P and X. Just the shaded part is the neighborhood of P and Y. And the shaded part is just the intersection of this whole circle with Y, right? This is the relationship, and this relationship allows us to go here. Okay. Okay. Thank you. Now, it's tough. The set notation gets really tricky. So you got here, and we assumed this. So this point that exists. So P, this P that is in Y, not in E but in G, this P is in Y and G, right? So P has to be in the intersection of G and Y. But P is not in E. So actually, I should not put P here. Let's put Q. Oh my goodness. Q. So there's some Q that is in the intersection of G and Y that is not in E. And G and Y is this set. So this means that there is some P in E such that Q is in. Is this fine? So we assumed. So we got this result, and we're trying to prove that E is equal to the intersection. So E is not a proper subset that is contained. So if we assume that these two are not equal, there must be some Q in Y such that Q is not in E but in G, because if we have G, E, and then G and Y, we're trying to prove that there's nothing in this space in between to prove that these two sets are equal. So if we assume that there is some point Q that is not in E but in G and Y, then this Q must satisfy this, right? It's in G and Y but not in E. And since G and Y is equal to this, there must be some P in E such that Q is in NRP. Okay? And if you just go back to how we defined this radius RP, NRP is a subset of E. So Q is in E. But we just said that Q is not in E, so this is a contradiction. Which means that there cannot exist a Q that in between these two sets. So these two sets just has to be equal. So E is equal to G and Y. Okay. Okay, this is the hard direction. The other direction is a lot easier. For the other direction, we just have to prove that for any G open in X, the intersection of a G and Y is open in Y. And to prove this, just note that for any P in EG, there exists a radius R such that, right, is a subset of G. This is just G is open in X. This is the definition of open sets. And if we just take the same neighborhood, this time in Y, right? Actually, let's write like this. So you guys get this, right? This is the relationship that we used before. And this must be in G and Y. So NRYP is in G and Y. For any P in G, we can construct some neighborhood in Y such that it's contained entirely within G and Y, which means that G and Y is open in Y. Okay. So really where this theory of open and closed sets is applied most is with compact sets. Oh, we're moving on to compact sets, right? Yeah, compact sets. Compact sets, and we'll use the open cover definition of compactness. So if you have a metric space X and some subset E in X, an open cover is a collection of open sets. What is SM? Is a collection of open sets such that E is in the union of Sn. So if you have a set E, an open cover is just a bunch of open sets that covers E. It literally just covers this set E. And this can be an infinite collection. You can just use an infinite number of open sets to cover E. This is, yeah. Open cover is fine, right? Okay. And E being compact means if every open cover contains a finite subcover. So let's think of it like you have a set E and we have this infinite number of open sets that cover E. Finite subcover means you can choose finitely many of these open sets such that it is still a valid open cover of E. So I can choose finitely many indices A1, A2, AN such that E is contained within you can choose finitely many of these sets such that it's still an open cover. Does that make sense? Okay. And compact sets, this definition seems very arbitrary at first, but compact sets have some very interesting properties. First of all, so with open and closed sets, we had, it was very tricky to move between metric spaces because something could be closed in a metric space, but not closed in this larger metric space, and it was this whole mess. But compact sets are very nice in that if you have this metric space X and a smaller metric space Y, then K is compact in Y if and only if K is compact in X. We can move between metric spaces without worrying about this thing being compact or not. If it's compact, it's always compact, no matter which metric space it's contained in. Okay, I should probably prove. So assume K is compact in Y, then we'll prove that K is compact in X. And this is where we use that theorem with transferring open sets. So let's Sn be an open cover of K and Y. And we can choose a finite subcover because K is compact. We assume that that's true, right? So we can, there's a finite subcover of Sn that entirely covers K. And if you remember our last theorem, it says that for any Sn, we can choose some Gn such that Gn is open in X, and the intersection of Gn and Y equals Sn. This is the last theorem that we just proved. So for any open Sn, we can choose this. Then Gn is an open cover of K in X. Because Gn, okay, Gn is like Sn plus a few elements. Gn is an extension of Sn, right? It's Sn plus a few elements. So if Sn is an open cover, then the Gn also has to be an open cover, right? And because this is a finite subcover, there is some finite collection that is an open cover. There's this finite subcover, which we denote from S alpha 1 to S alpha n, that contains K. Then the same finite subcover works with G. Because these G's are just an extension of the set S alpha I. If these S alpha I's are a cover of K, then the G alpha I's must also automatically be a cover of K. And these GNs are open in X by the way we just constructed. We worked that out in that last year. So I realized I proved, okay, hold on. I think I proved the opposite direction, right? Yeah, I proved the opposite direction. Okay. Oh my god, that was a stupid mistake. Oh my god. Let's take like a 5-minute break while I figure this out. Kevin, go. What's the quickest way to fix this? Yeah. So we want to prove this. It's compacted. Oh, okay. Okay. This. Okay, it's valid until here. Thank God. Okay. So because K is compact, okay, so never mind. So we're assuming K is compact in X, and we're trying to prove that K is compact in Y. If we let Sn be an open cover of K and Y, then we can choose these extensions Gn such that the intersection of Gn with Y is Sn. And because K is compact in X, we can choose a finite subcover. Let's say I equals N G alpha I such that K is entirely covered within this set, right? And by this intersection, the intersection of K and Y is contained in S alpha I, right? You guys get this? We just take the intersection with Y. But since K is just a subset of Y, this is just equal to K. So K is covered by this finite subset of the S's. And S was an arbitrary open cover of K and Y. The logic is a bit tricky. So we have an open cover in Y. We extend this to X, use the compactness of X to show that there's a finite subcover, and then we move back down to Y. So we're continually jumping between metric spaces. Okay. So, and then now we show the other direction, that if K is compact in Y, then K is compact in X. So for any, let Sn be finite subcover of, oh, what am I saying? Let Sn be an open cover of K in this bigger set X. So Sn is a cover of K in X. We want to show that there's a finite subcover of Sn, right? And now instead of, so here we jumped from Y to X, here we jump from X to Y. So we just let Gn be the intersection of Sn with a smaller space Y. And by our past term, we know that this is an open set, right? And by the definition of an open cover, K is contained within this union of Sn, which means the intersection of K and Y is contained within the union of Gn. This is just taking the union with Y. Yeah, and since all of the Gn's are open, this is a open cover of K in the smaller space Y. And because K is compact in Y, there's a finite subcover of Gn in Y. So there is a finite subcover that satisfies this of G's. So we jumped from Y to X and we used, sorry, we jumped from X to Y and we used compactness in Y to obtain this result. And now our step is to jump back up to X, which is just this step. Because if you remember, the S set is just an extension of the G set into the Y metric space, right? So we started with an arbitrary open cover of K in X, and we ended with a finite subcover. So K is compact in X. The compactness transfers between metric space. Okay.